Before we move on to illustrated example problems, let's discuss grounding and circuit protection practices. Recall that pilot voltage is ordinarily provided by a step-down transformer in the case of AC pilot voltage, or a DC power supply in the case of DC pilot voltage. Circuit protection devices like fuses can be incorporated in the high, low, or both sides of the control transformer, or the input or output of the DC power supply. Systems using ungrounded pilot voltage are sometimes referred to as floating, and that there is still a voltage differential between the left and right vertical upright, but since it's not referenced to ground, any voltage measurement employing ground as a reference is essentially meaningless. Any voltage measurement on pilot devices must therefore use 2 points with some electrical reference internal to the floating system. If, however, pilot voltage is to be grounded, it is customarily done so on the right-hand vertical upright. Now, any ground connection can be used as reference for a voltage measurement. Grounding one side of the ladder logic diagram serves other purposes, as we'll soon see. Grounding the right-hand side of the ladder logic diagram reinforces one of the earlier rules we discussed in the basic ladder logic lecture. Switches on the left, outputs on the right. This is to suggest that ladder logic always uses high side switching arrangements, and that the closure of a series path from the high left rail to the low grounded right rail energizes the output device in each rung. This is sometimes called sourcing, and that the closure of the switch connects the grounded output device to the source. This is in contrast to a low side switching arrangement with outputs on the left and switches on the right. This is sometimes called sinking, and that the closure of the switch connects the output device at system voltage to a path to ground. Safety considerations dictate the preference of high side over low side switching arrangements. Consider an errant connection to ground in the high side switching arrangement. In this case, coil A couldn't care less about this errant connection since its A2 terminal is already at ground via the grounded upright vertical rail. The A coil remains de-energized. Now consider the same errant connection to ground in a low side switching arrangement. In this case, the A coil has a path to ground in parallel to the open switch. Coil A energizes despite the switch being open. Low side switching allows an errant path to ground to unexpectedly cause a fluid power actuator to move or to start a motor. This is to be avoided, and the reason why high side switching arrangements with switches on the left and outputs on the right are preferred. The one exception to this rule is the overload contacts associated with motor starters. Grounding the right-hand side additionally serves to ensure the proper operation of circuit protection elements. Consider a DC power supply with fused output providing pilot voltage to a high side switching arrangement. Consider the repercussions if an errant connection to ground was made not at the A2 terminal, but rather the A1 terminal. With a switch in the open state, coil A would still remain de-energized. If, however, an operator closed the switch, the errant path to ground in parallel to coil A would provide no opposition to current flow, and current would spike to great magnitudes. The circuit protection device on the high supply side would, however, detect this event and open as intended. Alright, that's it for new content. The remainder of this lecture will feature 3 ladder logic diagrams left as exercises for you to properly document. Here's example problem 1. I've already included a brief functional description on the right-hand side and properly identified devices and their associated contacts. Note the right-hand side upright rail is grounded. The ladder logic diagram uses high side switching, and the DC power supply has a fuse on the supply side. I've already numbered the terminals of the buzzer and the pilot lamp. I leave it to you to number the rungs, number the wires, and number the terminals of all devices, and numerically cross-reference logical elements and mechanically interlock switches. Again, don't worry about what this ladder logic diagram does. Just document it. By all means, pause the lecture and give it your best shot. If you number the rungs correctly, your ladder logic diagram should look like this. If you numbered the wires correctly, your ladder logic diagram should look like this. Note that I'm using my preferred technique where the right-hand vertical upright is wire number 2. If you number the terminals for CR1 correctly, it should look like this. Note the coil terminals are A1, A2, and we're assuming that this is an ice cube relay with single pole double throw transfer switches. CR1A is the first contact, and it is normally open in nature. The left side is terminal 1-1, the right side is terminal 1-4. CR1B is the second associated contact. Since it is normally closed in nature, its terminals are 2-1, 2-2. Note that the float switch is a normally closed switch being held open via the gravity convention. As such, the terminal numbers would be 1-2 and not 3-4 for an ordinarily normally open switch. If you didn't clue in on the gravity convention, the comment on the right-hand side should have been sufficient. I'd like to say I did this as a teaching moment. However, I really just wanted to see you walk into a tiger trap and watch you die a slow, horrible death. Remember, the gravity convention dictates the switch's deactivated state. The schematic is drawn such that gravity would ordinarily pull the switch closed. However, it's being actuated into its activated open state by being immersed in liquid. It's for this reason that I ordinarily use the arrow convention that makes it explicit and obvious the normally closed float switch is being actuated into its activated open state. Don't walk into this tiger trap again. I guess I did teach you something in a twisted, devious sort of manner. If you numerically cross-reference the logical elements in mechanically interlocked switches, your ladder logic diagram should look something like this. Rung 1 has 2, underline 4. Note the underline 4. This means something closes in rung 2 and something opens in rung 4 when rung 1 is energized. Here's example problem 2. I've already included a brief functional description on the right-hand side and properly identified devices and their associated contacts. Note the right-hand side upright rail is not grounded, meaning pilot voltage is floating. Still, the ladder logic uses high-side switching, and the control transformer features fuses on both legs of the primary. The one exception to the high-side switching rule being the normally closed overload contact, which I've already numbered the terminals 95, 96. I've also already numbered the terminals of the primary contactor and overload relay. I leave it to you to number the remaining rungs, wires, and terminals of all devices and numerically cross-reference logical elements and mechanically interlocked switches. By all means, pause the lecture and give it your best shot. If you numbered the rungs correctly, your ladder logic diagram should look like this. If you numbered the wires correctly, your ladder logic diagram should look like this. Note I'm using my preferred technique where the right-hand vertical upright is wire number 2. If you numerically cross-reference the logical elements, your ladder logic diagram should look like this. Note that when rung 1 is energized, something in rung 2 closes. The normally closed manual buttons would receive terminals 1, 2. The normally open push buttons would receive terminal numbers 3, 4. The auxiliary M1 contact, being normally open in nature, would receive terminals 1, 3, 1, 4, and the M coil would have terminals A1, A2. Finally, if you're up for it, here's example problem 3. Note I did not include a brief functional description on the right-hand side because I don't want to confuse the heck out of you. However, I did properly identify devices and their associated contacts. Note I'm not using a color scheme for this particular example problem. I leave it to you to number the rungs, wires, and terminals of all devices and numerically cross-reference logical elements in mechanically interlocked switches. Let's assume all the control relays are 11-pin ice cube relays with single-pole double-throw transfer contacts. By all means, pause the lecture and give it your best shot. Good luck. You'll need it. If you numbered the rungs correctly, your ladder logic diagram should look like this. If you numbered the wires correctly, your ladder logic diagram should look like this. Note that I'm again using my preferred technique where the right-hand vertical upright is wire number 2. If you numbered the terminals correctly for control relay CR1, your ladder logic diagram should look like this. If you numbered the terminals for control relay CR2 correctly, your ladder logic diagram should look like this. Since we're currently discussing these logical elements, we might as well go ahead and numerically cross-reference these also. To numerically cross-reference rung 1 indicates that when rung 1 is energized, something in rung 2 closes, as does something in rung 4. The numerically cross-referenced rung 4 indicates that when rung 4 is energized, something in rung 3 opens. Note the underlined 3. The normally open manual start push button would get terminal numbers 3, 4, as would the normally open pressure switch 1 and the normally open limit switch 1. The normally closed proximity switch PX1 would get terminal numbers 1, 2. Note that the mechanically interlocked limit switch 2 is being actuated into its activated condition. This can be made explicitly clear using the arrow convention. Similarly, note that the normally closed proximity switch PX2 is being actuated into its activated open condition. An arrow convention makes this explicitly clear. The normally closed terminals of the limit switch 2 being held open would therefore get terminals 1, 2, and the normally open terminals being held closed would get terminals 3, 4. Similarly, the normally closed terminals of PX2 being held open will receive terminal numbers 1, 2. If proximity switch 1 and 2 were part of a 3-terminal single-pole double-throw transfer switch device, you might see these terminals called 1, 1, 1, 2, where the 1, 1 terminal is the common and the 1, 2 the normally closed side. Let's assume all solenoids have terminal numbers 1, 2, where terminal 1 respects the required polarity of this DC pilot voltage. Finally, let's ditch the ugly dashed mechanical interlock, numerically reference the mechanically interlocked limit switch 2. Note the normally open side being held closed in rung 1. When this reopens, something in rung 3 recloses. Note the normally closed side being held open in rung 3 indicates something in rung 1 reopens when this side recloses. Alright, this about wraps up our introduction to ladder logic documentation. These skills might seem confusing at first glance. However, there really is a system behind it, and it simply takes repetitive exposure to the system to figure it out. A properly documented ladder logic diagram leaves no doubt as to what particular function, rung, wire, terminal, and device a technician is referencing and how it influences other rungs, logically or mechanically. If you require more practice in this skill, you will be afforded ample opportunities to do so in later lectures. This lecture series would be prohibitively long if I documented every single ladder logic diagram, and most of the following lectures use undocumented diagrams as opportunities for you to put this skill to use. In conclusion, this lecture introduced ladder logic documentation. We discussed annotating the description of functional blocks, rung numbering, 2 different methods of wire numbering, terminal numbering, device and associated contact identification, and numerical cross-referencing logical and mechanically interlocked elements. Finally, we discussed grounding and circuit protection practices. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.